Huffman. So this one will be more interesting. Again, A, B, C, D. This time there are 5 symbols. 0.35, 0.25. 0.2, 0.12, 0.08. So initially we have 5 nodes in the tree. A, B, C, D, E. Okay. Somebody, which are the first 2 nodes we merge? And what is the probability of the merged node? Okay, so the answer is D and D. And so let's merge D and D. Okay. And what is the probability of this new node? Let's call it N1. 0.2, right? Why 0.2? 0.12 plus 0.08 is 0.2. Good. Now, what are the next 2 nodes we merge? Some people are whispering very low voice, please. Am I hearing C and N1? Okay, let's merge C and N1. Let's call it N2. What is the probability of N2? 0.4, because 0.2 plus 0.2 is 0.4. Okay, next one. Okay, I heard N2 and B. Anybody disagrees? Yeah. So now you have 3 nodes left, right? You have N2, which is 0.4. You have B, which is 0.25. You have A, which is 0.35. The 2 lowest ones are actually A and B at this point. So you merge A and B. Right. You get N3, which has probability 0.6, because 0.35 plus 0.25 is 0.6. And now you can just merge these 2 guys, get the last root node. You get 1.0, right? And then assign like this guy. Right. Let's actually write down the code words so that there is no confusion at all. A, B, C, D, E. Okay. Code word for A. 0, 0. Code word for B. 0, 1, right? Because we drew it in a different way, right? The root is actually on the right, so you need to go from right to left. So B is 0, 1. C. C is 1, 0, right? D. Yeah, 1, 1, 0. And E is 1, 1, 1. Right. We see it has the usual, like the properties, the optimality properties we discussed just now, right? That the 2 longest code words are D and E, and they have the same length. That's good. And you can verify that if one guy has higher probability than the other one, then it has a equal to or smaller length than the other one. So it satisfies the optimality properties. Okay, any questions about the construction? Very simple construction. Really not that much to say. It's try to implement it if you want to do coding practice for some interviews or so on, right? It's a very classic greedy algorithm. See what data structures you use. Do you use recursion or do you use iterative and so on? So why is it optimal, right? Just satisfying those 2 conditions doesn't make the code optimal. You need to prove that it is actually optimal. We will not prove it in class. So we will see the lecture notes. Actually, it's not in the lecture notes. You need to see the book. So you see Cover and Thomas chapter 5 for the proof of optimality. It's like based on an argument which is roughly that A, B, C, D. Okay. So it's like an inductive argument that optimality of this guy is equivalent to so it's like a step-by-step proof where you say that if my final code is optimal, that's if and only if the code at my second the second step is optimal, which is optimal if and only if my code at the third step is optimal. And at the very end, you're just left with two nodes because the last two nodes are just 0 and 1. So that is definitely optimal, right? So it's that sort of inductive proof where every step you show that this step is optimal. And at the end, you get to the base case, which is optimal. Will not do it. You don't need it for the homeworks. It's interesting. Read about it. Greedy algorithms you will often see like the proofs are sometimes a bit tricky. So this is one of them where like you need some amount of like math writing to prove it, but fundamentally this is the idea. So the first thing, as you might have observed, it's a greedy algorithm, right? We don't try to like do some sort of global optimization. At every step, we just take the two smallest things, merge, two smallest things, merge, so on. So that's something. Works for general Wi is greater than equal to 0 to solve this sort of problem. Like if you have any weighted optimization problem, right, they need not be probabilities is what I'm saying. You can take any W's and it's the same algorithm, it doesn't matter. So sometimes you will see applications of Huffman codes beyond just coding in some other areas. You might see some of them in either this or the next homework. And one last point is, this will be very important for this homework, so just be very careful. The tie breaking, right? We said that like if you have two possibilities, then like if you have three nodes, each of them have 0.2, 0.2, 0.2. You can either merge the first two or the second two or the first and the third. So there is a non-determinism sort of built in. The construction is not deterministic. In many cases, you can have more than one possible optimal Huffman code. So when you do the homework problem 5, be very careful. Last year, lots of students have a lot of issues. So just be careful that the tie breaking step in particular means that you have multiple possible Huffman codes, right? All of them will have the same expected code length. All of them are optimal, but they are different. Okay, last thing, let me go back actually here. No. Okay. Last thing is that for Shannon codes, we saw that expected code length is between hx and hx plus 1. For Huffman codes, that's basically what we have. We know, maybe let me write it like this. So we know that hx greater than equal to expected length of Huffman codes, which is less than or equal to expected length of Shannon codes, which is less than hx plus 1, right? So this is sort of the chain of inequalities. So Huffman codes are somewhere between Shannon codes and entropy. For certain types of distributions, you can prove stronger results, but really this is what you have. Okay, coming back to the construction. Can somebody suggest how do I do this step? How do I always pick the two nodes with the least probability? Can I do it in an efficient way? Maybe even in inefficient way. Just any ideas on how we can pick the two nodes with the least probability? How would you do it if you were implementing it in Python, let's say? Yeah, correctly suggests that you could use a heap or a priority queue, which is a data structure where you can always pull out the lowest thing or the highest thing depending on the type of heap or priority queue you're using. If you're not seeing those, it's fine. Just you should be aware. There is an inefficient way, right? You take the list of nodes, you sort it. You take the two lowest ones. Then you add the new node, the N1 node, and then you again sort it, and then you again take the two lowest. That also works. It's less efficient, but it works. Heaps or priority queues are, I guess, easier. Another thing to note is that in many situations, you will construct the Huffman code once and use it multiple times. So it's fine if the construction is a bit slow, because ultimately, like, you're going to construct it once for a distribution and then keep using it for lots of symbols. Okay, let's actually look at a code for constructing this in the library. Let me know if I need to zoom at some point. So we go to SCL, we go to compressors, we go to Huffman coder. Okay. Right. I'll sort of walk you through it. The file is this one, Stanford compression library, SCL compressors Huffman coder.py. Right. So that's the file if you want to later look. So what we do is we define this thing called a Huffman node, where the Huffman node has a less than equal to implementation, which just says self.prob less than equal to other.prob. So basically what we are saying is you are creating this class in Python, which has this ordering property that you can define which node is bigger than the other node based on their probabilities. Okay. So then there is a function called build Huffman tree, which is what we were just doing. So let's see what the function does. If the length of the alphabet is 1, right? So if you're at the last node or there is just one node, there's nothing to do. You just, that's sort of the base case, I guess, of the recursion. What else? You start with a node list equal to the empty list. So I'm here. Yeah. Okay. Then you, for A in self.alphabet, you create these nodes and you append them to the node list. And then you use this function called heapify, which converts this thing into a heap. Right. And then you have a loop where while the number of nodes in your heap is more than 1, you first heapify the thing. Then you take the two smallest symbols, right? Very easy. You pop from the heap. And then you create this combined symbol, which we were just talking about, right? So the last 1.prob and last 2.prob. You create a combined node and you push it back into the heap. And at the end, you're left with a single node, which is the root node of the thing. Right. So basically the construction we saw, you can very easily code it up in like less than, if you remove the comments, it's like less than 10-15 lines of Python really. So very simple. And any questions on this? Okay. Yeah. So depending on whether you you learn easily with code or with like this sort of pseudo code, you have both options available. So one topic which again connects to the homework question 4 is decoding So if you remember, we in lecture 2 actually we talked about like you have these prefix codes, they can be represented with trees, so the decoding is so easy, right? You just walk down the tree, you decode a symbol. We were very happy, right? So we talked about this tree-based decoding, right? Where the idea was very simple, really. You have this tree like this, 0, 1, 1, 0. And then you had like a stream which was like 0, 1, 0, 1, 1 sort of thing. And then you would like go here, then you would go like this, and then you would go like this, and then you would decode it, right? Yeah, sadly, like nobody uses this. This is not a good idea in practice. 2 reasons. One is there are too many branches. Branches in the sense that if you write the Python code for this, there is like if-else statements. Like if this is 1, go left. If this is 0, go right. That sort of branches, right? So like this sort of thing. If 0, left. If 1, right. And branches are really, really bad for modern computers. So modern like computer architectures. We won't do a computer architecture course right now, but in short, the reason is they do something called pipelining, where they sort of collect a bunch of instructions and try to execute them in a pipelined way. And if you take the wrong branch, then you have to flush the whole pipeline. A lot of work goes to waste. So it's just bad. Like branches are bad. Even though you have good branch predictors, still branches make your code really slow. And you might wonder, like, why do we care, right? Do we really like decode so much data with Huffman? Actually, we do. Like gzip, one of the most popular compression formats, uses Huffman as its entropy coder. And every time you download a file from the internet, there is probably a Huffman coder running. The older video codecs used to use Huffman. Newer ones, I don't know. Every time you're streaming a video over YouTube, either this or something similar is actually running. You're always decoding a prefix code. Like anytime your computer is running, you're probably decoding a prefix code somewhere. So this is not just about Huffman, right? This is about any just this tree-based decoding is a really, really bad idea. Because of these branches, you will never get the same sort of video throughput that you get today. So let's look at an alternate way. We'll look at it briefly now, and then later in the homework, you will actually implement the decoding. This is question 4 of the homework. Oh yeah, you implement it in the context of Shannon codes, but the idea is like the same. So I will briefly describe it so that you have some context when you start the homework question. So there is a decoder state table, which is like 0, 0, 0. Actually, let me draw code here. So we draw this code. A is 0, B is 1, 0, C is 1, 1, 0, D is 1, 1, 1. Okay. So this is decode state table. And then you have another table which is called encode len, which is A, B, C, D, 1, 2, 3, 3. Anybody wants to guess what the decode state table is doing? This is all corresponding to the code I made on the right, the A0, B10, that one.
You basically just grab 3 bits at a time from a sequence and then check, which symbol it corresponds to in the decode state table. And then from there we can
Yeah. So this was basically the full answer. So let's start step by step, right? So what does it mean that what does it mean that 011 is decoded to A? What does that mean? Why are there like 4 things? 000 is decoded to A, 001 decoded to A, 010011. Why are all 4 decoded to A? Just try to guess. I haven't obviously told you what we are doing. But if you had to guess.
So if 86 is A, like 0, it can only be encoded to A.
Yeah, so the answer is you look at the prefix, right? Like just the way we were doing the prefix coding, prefix decoding in the past. You look at a sequence, right? And you try to find like the first symbol that you decode out of it. So if you see a 000, the first symbol you would decode out of it is a A. It starts with 0, that's the only code word that starts with 0. If you see a 100, if you see a 100 or a 101, the first symbol you would decode is a B, because the B is the only one that starts with 10. Right? If you see a 110, then you would decode a C. If you see a 111, you would decode a D. So, with sort of this in mind, you can like define, you can implement this sort of function. I think this is actually not what you are asked to do in the homework. You are asked to construct these state tables in the homework. So, I'm not infringing upon your homework here. So this is, we call it decode symbol fast in the sense that it's faster than doing it in a tree. So you define this state, which is you take the 3 bits from the bit array, the next 3 bits from the bit array, you look at the decode state table, and you can decode a symbol already. Like you can decode that based on the 3 bits, you can decode the symbol. And then you look at the encode len table, which tells you the length of the encoding. And then you can like basically return S and the number of bits. So it's like a few steps of things to do. First thing is you take the 3 bits, next 3 bits from the bit array. Based on those 3 bits, you decode one symbol, only one symbol. So you can decode any of these ABCD symbols. Then based on the symbol you decode, you check how many bits do I actually need, like how many bits I have actually read. And then you basically advance. So that's sort of the process. And you will get much more practice with this in the homework, but here I just wanted to give you a flavor. Any questions on this? And if there are no questions, can somebody tell me what this 3 is? Why 3? What's so special about 3? Yeah, I hear that 3 is the longest code word here, right? Yeah.
I have a just question.
Yep.
What situation would we have this bit array with symbols of 3 when we're dealing with the prefix code? Like it just seems.
Yeah. So the way to think about it is that you are given a long sequence, right? Like it's just a stream sort of coming in or a big block or something, right? You have encoded like a bunch of ABCDs together. You got like a long bit array. And then you take the first 3 bits. Based on that, you decode one symbol. And you know that you have read maybe 1 bit. Maybe it was an A, so you only read 1 bit. So next time you will look at, so if the first time you look at bit 1, 2, 3, next time you look at bit 2, 3, 4. And then maybe you read 2 symbols. So now you have consumed bits 2 and bits 3. So now you look at 4, 5, 6. So that's sort of the progression.
It's just not clear to me why that array would even exist in the first place. Like what is the...
I think we talked about it a little bit earlier. I think as you do the homework, you will get more experience. But see, the whole reason why we talk about all these prefix-free codes, why do we need prefix-free codes? Why is it not sufficient that ABCD just have different code words? Why the prefix-free property? It's because almost all the time you don't want to encode just one symbol. You want to encode a long string of symbols. So the thing you encode is like A, C, D, B, B, D, D something. And that whole big thing will be converted to a long bit array. So like 0, 0, 1, 1, 0, 1, 0, whatever, right? So you get this long thing. And then that long thing you should be able to decode back to the original sequence. Look at the lecture 2 slides where we talked about, like there is an alternate approach like in a Morse code or something where you put a comma or a separator between every symbol. But that's not how we do it typically. It's not optimal. So it's better to do like, have it prefix free so that you can encode a long sequence into a long bit array. So that's how you get the 3 basically. At the very end, right, like you might reach the very end of the thing where maybe you don't have, like it's not a multiple of 3 or like there is some boundary conditions. So you can sort of pad it with zeros just to make sure it works out.
I wanted to just clarify the last point that sure, like there may be some edge cases, boundary conditions. So suppose you are encoding AB 010. In that case, you read 3, you decode it, say you can only decode one symbol. You are still left with 10. But that's just a corner case. You can just always append last bit as 0 if it's not a multiple of 3. Read 100 and that's B again. That's where you stop the decoding.
Yeah. So Pulkit is talking about padding basically, that at the end you might not be left with 3 symbols when you decode a long sequence. You just pad it with zeros. It's fine. Okay. Any other questions? Sorry. So one more thing about a couple more things about table-based decoding. So the size of the table is exponential in the maximum depth of the tree, right? We saw that in the last one the table size was 8 because 2 power 3 is 8. And what you want is, like in practice, you want it to fit in your cache. So it should be very small so that your decoding can work very fast. So therefore, you want to limit max depth. So this is something we will not do in class. Last year, a couple students did it actually as a project, but there is something called a constrained Huffman code, where the idea is best code with max depth constraint. The construction is slightly more complicated than your usual Huffman codes, but these are the version of Huffman codes that you will often see being used in practice. You want to constrain the max length, and often you want to constrain it to like 16 or 24 or like a byte multiple thing, so that it works nicely with like how computers work. Any questions on this? Yeah. So this is like really low level stuff, but you will see a lot of action in compression is often in the very low level stuff. You have a good algorithm, that's good, right? But if it uses all these complicated trees and so on, you can't use it for the large volumes of data. Videos are huge, logs are huge, text is not that big. So if you're just compressing text, go all in. But like for practical types of data, it's often like so big that you can't afford like suboptimal types of things. Last thing, just on table-based coding, the last thing, table-based decoding. More of a homework, really. Does anybody recognize this sequence? Yeah, some people are correctly answering it's the Fibonacci sequence, right? What is the sum? So 1 plus 1, 2, 2 plus 2, 3, 4, 4 plus 3, 7, 12, 20, 33, right? So we make this probability distribution. make this probability distribution. Just make the Huffman code for this at home. What you will observe is that this is like an adversarial case where you will get really, really long code words, right? Like you might think that why worry about this max depth? In practice, you will never have a very long code word. All the code words will be short and so on. But there are these special distributions where you will see that the max depth in this case will be basically equal to the number of symbols, or that minus 1, something like that. So the max depth will be roughly equal to the number of symbols. So you will get a really, really long code word like 1, 1, 1, 1, 1, 1, 1, 1, 1, so on. So solve it at home. Hopefully you enjoy it. Okay. Moving on to some practical Huffman codes. So first thing, this is like somebody did a nice experiment where they took a keyboard and the height of the letters on the keyboard are the frequency of that symbol. So E is like very, very high, T is the second highest, A is the third highest, right? So just in English. And then they also made this Huffman code for this distribution. And you can see at the top part, for example, that, sorry. Okay. Yeah, so E you see, E is like very short code word. Z, Q, X, J, like the less commonly used letters in English, are much longer, right? But it's non-trivial, right? If you didn't know the algorithm, like this is the optimal code for this distribution. So just something. At home I did a few more using SCL. So I followed basically Pulkit's tutorial of SCL. I installed SCL. I downloaded this very famous book, which I guess you know, Huckleberry Finn by Mark Twain. Right? Oh yeah, let me make it a bit bigger. Yeah. Right. So it's an English book, right? Normal English text about treasures and so on. And then I used SCL to create the Huffman tree for this distribution. We will post this and take a look, but you see like the letter small e is like very short code word. Letter capital E, the uppercase E is like much less common, right? Because E is very common, but E doesn't often come at the start of a word, of a sentence actually, right? Okay, we'll try to scroll down. Then what I did was I actually used sorry, this is just hard to do now. Is it visible? No. Okay, yeah. So I actually compressed it with the Huffman code. So I started with a 622 kilobyte file, 622542. It got compressed to 348142. So nice. With Huffman codes now you like can compress this one book to about like you can reduce it by 44%. So that's good. Okay. Then I thought like maybe let's compress another file. So I took this Apache Camel, which is a Java library, and which looks something like this, like you have these function calls and semicolons and symbols that don't occur as commonly in English, but they occur more commonly in code. And when we get there, we'll see. Okay. So one thing you see here is that, see this parenthesis, right? These parentheses get a much shorter code word than they would have gotten in normal English, because a code has many more parentheses than like English. And similarly, semicolon is like much shorter code word. The semicolon you see right below the parenthesis. So depending on your data distribution, your Huffman code will look very, very different, right? And that's the beauty of it. Like any distribution, you create the optimal code for that distribution and then use that one. Okay. Last one. Okay, here also I tried to compress it. This one compressed by about 40%. The last thing I did was I took an encrypted file. So the encrypted file was not, it's bytes, right? It's not like human readable English. So I made the Huffman code on the bytes. Look at this Huffman code. Anybody tell me what do you see in this Huffman code? Yeah, you see that all of the symbols have same depth, right? They seem to have all the same depth. Can anybody explain why the encrypted file gives me this strange looking Huffman code? Why did all code words get the same length? This is basically the fixed length code that we saw in the first lecture.
If it's not like this, then you can basically map it back to English word.
Yeah. So typically, like most encryption algorithms, what you will see that their output is IID uniform sort of, so it's uniformly spread across the bytes. And the reason is something like it should not leak any information about the original distribution. So that's why all inputs go to the uniform distribution for a good encryption algorithm. Here I think we used AES, which is like one of the state-of-the-art encryption algorithms. See, you see all of these, the whole tree, everything is of the same length. So just use, so one lesson here is that like you can't compress encrypted data, right? You have like this, there is just some fundamental incompatibility. Like after encryption, if you want to compress something, do it before encryption, not after encryption. Because encryption will basically destroy all structure in your data. The data will look completely random to any compressor. It will not get any compression at all. So if somebody comes to you, right, with a startup idea, I can compress every file you give me by 50%, give them a encrypted file, see what they do. And I guess if they're able to compress that encrypted file, that means they have like broken AES. So that's a good thing. Most likely they won't. Okay. Is that clear that the encrypted data is random? It's like IID uniform. It's not exactly IID, but it's close to IID uniform over all the bytes. So 0 to 256. So you will spend basically 8 bits per symbol there because each of the byte is equally likely. Okay. Right. And then I actually ran the compression right here. I think you can sort of see. Let me try to zoom in. Basically, you get compression rate of 1, which means that there is no compression at all for the encrypted file. So this is a we'll post the slides. Okay, so there are a couple more things about Huffman codes that we will not try to cover today. We will wrap them up in the next lecture. But after we cover those very small topics, the next lecture will mostly be about theoretical intuition behind entropy and block coding. Why entropy? What's the importance of entropy? Why does block coding works? How does it interact with like large laws of large numbers, probability, and so on? So Tsachy, Professor Tsachy Weissman will be taking that lecture. And next week, we'll start talking about practical block codes or stream codes, which actually get very close to entropy. And they are the ones that are used like for the state-of-the-art, basically, compressors. So with that, thank you. Let me know if you have any questions.